Yes, and I'll show you the complexity of LIGO, and it's because we have three optical cavities, the two arms and the power recycling mirror, and then in addition we have a Michelson whose port has to be kept dark. We have 4 degrees of freedom. We use reflection locking to control 3 of them, and transmission locking to control the 4th.
I think I missed which one you're using, which of the 3 versus 1 that you're using.
So reflection locking, Pound-Drever locking, is how you control a Fabry-Perot cavity, an optical cavity, which are 3 of the 4 degrees of freedom that are important in LIGO. The 2 arms and the power recycling. And the transmission locking is for the Michelson degree of freedom.
So do you want to define carefully the Michelson degree of freedom?
Yes, and I will shortly. Okay. Okay. So in order to control these degrees, the transverse degrees of freedom, we also have a series of cavities before we ever make it into the interferometer to control the input beam. And these are the input optics, for example. We have a pre-stabilized laser. Here's our electro-optic modulator, also known as a Optical cell, which puts on this RF modulation. We have a little triangular optical cavity, which is called a pre-mode cleaner. Then we send the thing into the beam, and then to a mode cleaner, and then into a mode matching telescope before it ever gets into the interferometer. Why do we have such a complex system? Every one of these cavities can keep the beam that is transmitted stable, in the sense that it controls the frequency. It only allows light of a resonant frequency to be transmitted. If it's short, high frequency is emitted, but still stabilizes the beam in transverse profile and stabilizes the beam in terms of position and direction of the beam. And then you put in another mode cleaner, which is even longer, and now we have suspended optical components such that the mirrors are not moving so fast, and they will stabilize the beam even more in frequency by not letting frequency fluctuations pass through, because they'll fall outside the bandwidth given by the pole frequency of that cavity. So you can cascade more and more of these mode cleaners, and their jobs are to do, again, several things: to stabilize the beam's frequency such that only a narrow range of frequencies can get through and frequency fluctuations go away, to stabilize its transverse profile, and to stabilize its direction and position.
Both mode cleaners are locked with Pound-Drever Hall.
They're all locked with Pound-Drever Hall. And what makes life a little bit easier in the case of a triangular mode cleaner is that the reflected light is coming out this way. It's not coming out in the same direction as the incident light. So you don't need one of these Faraday isolators to get that light out and look at it. It's coming straight out in a different direction. Very convenient. Another thing about triangular mode cleaners is that the light is coming here, but it's polarized. If it's polarized vertically, then it bounces like this, comes through, and that's its total path length. And if that's an integral number of half-wavelengths, great. But if its electric field is this way, then as it bounces through, the electric field is this way, and then it's this way, and then it's this way. It is flipped direction as it goes around the triangle. And because it's flipped direction, it effectively means that there's been effective pi phase shift. And that means that the 2 different polarizations of the incoming light, only one of them can be resonant at a time, and the other won't be. And so we set things up such that this is a polarization filter, and the light comes out with one polarization only. Okay? Now, every time you have an optical cavity, you have a beam waist and an expanding beam. And here is a beam waist and an expanding beam. And every time you have cavities, you have to mode match. You have to put in lenses or reflective mirrors whose job it is to focus the beam coming out of here such that it's exactly matched into the beam here. And that's just optics, but it has to be done. Coupling from every cavity to every other cavity requires careful mode matching. I talked about mode cleaners just now. This back mirror is strongly curved. such that so it's producing a very tight waist over here, such that the transverse profile of the beam coming out is very, very well defined. And that has to be then mode matched into the interferometer.
What is clean and the mode cleaner?
That means we're throwing away any components of the light that are fluctuating in frequency, fluctuating in intensity, fluctuating in position or in direction, or in transverse profile. All those fluctuations get thrown away. They're dirt. We're cleaning up the beam.
To what extent can you actually suppress amplitude fluctuations? You don't get much suppression.
You don't get much suppression of amplitude, so I sort of misspoke when I said intensity fluctuations are also filtered.
Direction and transverse wave function.
It does average out amplitude fluctuations.
Yeah, it averages them out a little bit, so you get a little bit of filter. Yeah, storage time of the light. Yeah. You had a question? No?
Oh, so by transverse mode, you mean filter out the higher TEM ones?
Yes, that's exactly what we mean.
How does that work?
So a higher order TEM mode will have a Gouy phase shift that's different than the TEM00 mode. That Gouy phase shift, as it accumulates around a round trip, will not be an integral multiple of 2 pi if you arrange it to make sure that it's not, by changing the curvature of this cavity. You can change the curvature of this mirror such that it changes the size of the waist and the Gouy phase advance as you make a round trip. So you set it up such that it's not going to be resonant. Okay? Not just the TEM01, but also the TEM014 and everything in between. In fact, you can change the radius of curvature of that back mirror, and here's the total one-way length of that of a triangular mode cleaner, and call that the Gfactor. And you can and what you want is a Gfactor, which let's see. This is a plot of the total power. Or electric field amplitude, circulating in or transmitting through a circular mode, not even circular, any kind of a mode cleaner, as a function of that cavity Gfactor, and you see peaks. And where these peaks are caused by, accidentally, TEM01 has a Gouy shift. If you change the radius of curvature, you're changing the Gfactor, you're changing the Gouy phase shift of the TEM01 relative to the TEM00. And if it just happens to match pi, or pi over 2, or 2 pi, then you get a lot of transmission of that higher order mode, which you don't want. So you make a plot like this and plot all these peaks are different TEM modes, 01, 02, 03, all the way up to 016, and 88, which has the same phase shift as 016 and 16.0. And you choose a cavity Gfactor, which means choosing a radius of curvature for a given length. This is taking care of higher order modes resonate in the cavity.
So let's just back up, just so I understand it clearly. So what you're plotting here is
effectively the radius of curvature of that back mirror.
That's what's being plotted horizontally. You're showing the resonances for the various
higher order modes.
Various higher order modes.
And this is actually sort of an envelope curve. One really looks like this, and another really looks like this, and another really looks like this, and this is an envelope over all those TEM modes. M plus N. That's really all that matters.
So how high in order do you currently do this?
This is 16.
Up to about 16.
Yeah, and you're hoping that when you get to higher orders, I mean, there really isn't much of that coming out of the laser, okay? And that's true for the most part. Cavities after cavities within cavities. I mean, really, the LIGO interferometer, in order to make use of all these tricks, is a complicated optical device, a really complicated optical device, in order to be sensitive to something like 10 to the minus 10 rad phase shifts. We cascade optical cavities, each longer and more stable than the one before, to quiet the beam frequency fluctuations more and more, and the transverse profile fluctuations more and more over a wider and wider frequency band. Okay? So laser goes to the pre-stabilization of the laser, to the input mode cleaner, to the power recycling cavity, and then finally into the arms. These are separate resonant cavities. Separate resonant cavity here, separate resonant cavity here. But this is a resonant cavity that surrounds these resonant cavities. And in fact, for advanced LIGO, we'll have another one called the signal recycling cavity and an output mode cleaner as well. Every time you go from cavity to cavity or cavities within cavities, you need careful mode matching. And you need to be able to tune that in situ, because nothing ever works the way it was designed on a spreadsheet. Mode matching telescopes, I talked about them. Okay. How do we choose the transmission of the input mirror of the arms? This turns out to be a very important guy, because if you make the input mirror reflectivity very high, then the light can bounce back and forth. You're always making the end mirror as close to 1 as possible. If you make the input one very close to 1, there'll be a lot of bounces, a lot of gain in that optical cavity. But the cavity pole will get smaller. So as you increase the reflectivity of the input test mass, you're increasing the arm cavity gain, which means you've got a lot of light that will respond to a gravitational wave. So at low frequencies, your sensitivity to gravitational waves gets better. But and that's the DC strain sensitivity. But the pole frequency gets smaller. And so, ignoring all these other curves, just the black one, you can see that as the ITM reflectivity is increased, we improve our DC sensitivity at the expense of our high frequency sensitivity. And there's a family of curves that you can choose by choosing the input test mass reflectivity. So how do you choose it? You look at all the other curves. All the other curves have nothing to do with sensing the gravitational wave. And I'm ignoring radiation pressure, which does have to do with sensing the gravitational wave. But basically, let's look at the seismic noise, which is a wall, and the test mass suspension noise, which falls like 1 over f squared and has resonances due to the suspension resonances, and other things like that. You look at all those other noise curves that you really can't do anything about, or that you've done everything you can about, and then you choose your shot noise curve, which depends on the reflectivity of the input test mass more than anything else. And you choose it to maximize this region of sensitivity. And this is the first choice you make when you design a LIGO interferometer, is this. If, for example, for advanced LIGO, this seismic noise goes way down because we spend gazillions of dollars on seismic isolation systems, then you can afford to do this to sort of improve things in this regime. You might remember that gravitational waves, LIGO is in many ways optimal for detecting interesting gravitational waves, but really there aren't that many astrophysical sources out here at 1,000 hertz. There are lots of astrophysical sources at low frequencies. Of course, the reason why these intermediate frequencies that LIGO are sensitive to are so interesting is that's just where the binary inspirals merge. So that's really the most interesting place if what you're looking for is colliding black holes, which some of us are. So the game is to try to reduce, is to try to pick up this area around here, where LIGO can't really operate, but advanced LIGO can. And that will really tremendously improve our sensitivity to binary inspirals in this regime. Okay, and we do that, and when we do that in advanced LIGO, we're going to change the input test mass reflectivity. Yeah?
In that picture, what's the purple one that has peak at 10 hertz?
The purple one with a peak at 10 hertz? What the heck is a peak at 10 hertz doing there? Can't even read it.
It has a resonant peak highest one, just the highest on the left.
Yeah, this thing here you're talking about. I'm trying to remember. It's a crazy one, isn't it? What is this thing at 10 hertz?
Thermal noise, but the peak got to be...
No, the green is the suspension thermal noise. What?
Thermal noise goes up to minus 5 halves.
Yeah.
And should go F to minus 1 half below the resonance. That's not thermal noise.
Gee, I'm not even sure what the heck that is. I wish I could read this. Actually, I can read it over here. somebody did some really detailed calculation of some resonant frequency of a suspension, like I think that's the top plate of the of the suspension. I don't know.
Piece of metal. Okay.
Piece of metal that's vibrating at 10 hertz. Okay, let's talk about suspensions. I've talked enough about optics, and we've been talking for a long time.
This is what.
Sorry?
This looks like the one in a different place.
No, this is 1 hertz. This is 1 hertz. They all look like this, and there's a reason for it. Okay? Something vibrates. No, this happens to be at 1 hertz. This is 1 hertz. You can't read it, but you can read it. You'd read it if that thing was any good.
All springs look the same.
Yeah. So let's talk about suspensions. This is really a key, another key or core technology of LIGO. Have you guys give you a quick introduction? Much more detail. Phil Willems and others will talk about it. Okay.
On Wednesday, we'll start.
Okay, great. So a pendulum is really a beautiful mechanical filter, as is a mass and a spring. And the idea is very simple. Here's your mass. It's hanging on a pendulum. Here's a suspension point. Okay? The suspension point is moving with an x sub 0 at some frequency. The mirror is getting buffeted by noise at some force, maybe buffeted by air or something like that, and it's moving at with some position x. We want x to be small. It's going to be a function of the frequency at which, for example, you vibrated either up here or over here. Okay? Let's not worry about this one right now. Let's consider here. Why? Because every single effect of the noisy environmental world we live in, seismic noise, human noise, people coughing and walking around everywhere, is all getting to the mirror through this pendulum and nowhere else, especially if it's in a vacuum. Nothing else can touch this mass. The only things that really touch this mass are its own thermal vibrations, because it's at 300 degrees above absolute zero, the thermal vibrations of this wire, and the motion of the suspension point. That's it. Okay? Now there is a heck of a lot of motion up here. But look at its response as a function of frequency. If you move this thing very slowly, well, this guy will follow it. So the transfer function, which is the ratio of x to x0 as a function of frequency, is 1. X to x0 is 1 at low frequencies. Now do it at the resonant frequency, okay? You get the swing going at its resonant frequency. Now the response x0 is huge compared to, the response x is huge compared to x0. You move this thing at a resonant frequency and this guy swings wildly, like that. Then when you go to even higher frequencies, you're moving this will follow, but before this has a chance to follow, it's got some inertia because it's swinging on a wire, this guy has changed direction. And then it tries to catch up, and this guy's changed direction again. So at high frequencies, this guy can't keep up. And x over x0 falls. This is a log scale, and this is a fall off that goes like 1 over f squared. Okay? And what you see is that it's a mechanical filter. At high frequencies, this can vibrate with an amplitude of a micron. And this will vibrate with an amplitude 4 or 6 or 8 orders of magnitude smaller. It's a beautiful idea. And it's an idea that requires no control system. It's purely passive. And you can cascade it. Just take this guy and hang another mirror from it, and hang another mirror from it. And all the motion up here is attenuated by 1 over f squared here, 1 over f to the 4th here, 1 over f to the 6th there, as long as you're above all the resonant frequencies. As you cascade these, you get a coupled pendulum problem. You have more resonant frequencies. It gets more complicated. But above those resonant frequencies, it gets very quiet. Still, you do have this tremendous amplification at the resonant frequency, and that's bad. So what do you do about it? Well, the shape of this curve depends on how, let's see, if you're moving this by a little bit at its resonant frequency, this thing will move a lot because it's at its resonant frequency. How much is a lot? Well, in the absence of any energy loss, you can move the suspension point a little bit, and this guy will swing bigger and bigger and bigger and bigger and become infinite in amplitude, right? In the absence of loss. But there's always some loss. And because there's always some loss, it damps the motion, and it will limit the amplification Okay? But there's a price that you pay for this limiting of amplification by damping. And the price that you pay is that it's the fluctuation dissipation theorem, otherwise known as there is no free lunch. You reduce the motion at the resonant frequency and you get extra motion away from the resonant frequency. You get fluctuations at non-resonant frequencies due to dissipation or loss of energy at the resonant frequency. It's got to go somewhere. Okay?
So on Wednesday, Phil Willems will discuss this quantitatively.
Right. So we use this idea, we make use of this idea in many different ways in LIGO. One thing you can do is you can say, let's minimize the loss, which reduces this fluctuation away from the resonant frequency, and then at the resonant frequency, let's say we can tolerate it. So for example, we make our violin modes of those wires really very low lossy, such that they produce an extremely narrow but huge peak in our noise spectrum, and then we just don't look at gravitational waves in that frequency. Really. Or we can, for example, the test mass vibrates. It has some motion. Its motion is, a test mass is this big, and it's fused silica, and it vibrates at maybe 10 kilohertz. Here's a 10 kilohertz peak. It's huge up here, but we don't care. It's outside of the LIGO band. But we want to make sure it's a very low loss resonance so that the thermal noise really falls. And you'll see in the quantitative thing, it follows a power law over here. But the level of this power law depends on how narrow this resonance is, how high the Q, which is the ratio of the width, the position of the resonance to its width is the Q. Very high Q means you're putting all that thermal power in the resonance far from the LIGO band and not in the LIGO band.
So the constraint is that the integral of the current has to be 1/2 kT.
Yeah, you got to put 1/2 kT somewhere. Exactly. Exactly. So you can see either we can tolerate it in the band by making it narrow, tolerate it outside the band by making it narrow, but really, can we tolerate it at low frequencies? And the answer is no. And therefore, we have to, because this becomes huge and this thing kicks around at 1 hertz, at a 1 hertz pendulum frequency, and they'll throw us out of resonance. It's not even a question of noise in the interferometer. It'll throw us completely out of resonance and we can't do anything. We have no sensitivity then. So we have to take this peak and we have to damp it. But remember, if we damp it by putting in dissipation, it'll cause fluctuations at other frequencies. If we do it passively. But if we do it actively, we can buy ourselves a free lunch, so to speak. Okay, you get the sense of this? Yeah, you spend money and you get a free lunch. It's the way advertising works. Yeah, right. I mean, in other words, you can kill this thermal noise by actively damping it. And so we need an active feedback system which uses power, wall plug power, in order to damp these resonances. I think I said all this. Pendulums can be cascaded. Advanced LIGO mirrors will be suspended on quadruple pendula. I said all that. Mirror control. Seismic isolation system and the pendulum keep the mirror motion to a minimum. The mirrors are being kicked around by the environment, but they're not at high frequencies they're being isolated by this mechanical filtering. But being free, they may not be where you need them to be. And you need an active control system to keep the mirrors at their set points, separated by an integral number of half wavelengths apart, and you need to keep them there and not have their pendulum pendulum mode be excited to kick them off of there. So we need to damp them and we need to position them absolutely. And that means we need carefully designed feedback servo loops. So here's a suspension. It's a single suspension for initial LIGO. It's a box, maybe about yay big. Weighs a lot. It's got a big mirror in it. It's hung by a single thin piano wire. Piano wire is very lossless stuff. Okay, piano makers know what they're doing. The piano wire touches the mirror on the bottom which causes loss on the mirror motion, the mirror thermal noise, and that's bad. We try to minimize that by having a little standoff here, which you can't see. It's a little rod, and the wire touches the rod in a well-defined place, and that minimizes the amount of dissipation, so that when the mirror itself is vibrating thermally, that it's not being damped so much by the fact that there's something touching it. You know, if you touch a bell, you damp it and it stops ringing, and we want to minimize that. But in addition, on the mirrors, we glue little tiny magnets, 1, 2, 3, 4, and 1 on the side. Tiny. You don't want to touch this mirror, so you can put in a tiny magnet. In fact, it's on a standoff, which has a square millimeter surface area that we glue on. 1, 2, 3, 4, and 1 on the side. And then we surround that magnet with this thing here, which we call an OSM, which nobody knows what it stands for, optical sensor and electromagnetic actuator, whatever it's called. And it's doing two things. Here's the standoff. Here's a big mirror. Here's a standoff. Here's a little this little ceramic thing, and inside of it there's an LED and a photodiode. And as the magnet moves, it puts a shadow on the photodiode, and the amount of energy, the amount of electromagnetic energy hitting that photodiode is a measure of the position of this magnet. So it's a sensor. But in addition, it's got a coil, and you can run a current through it, and that will cause a force on this magnet. And that force will push and pull against the pendulum to move the mirror. So it's a sensor and an actuator in a compact little device, and the biggest price that we pay is the fact that we're touching the mirror in order to move it. And another price is that this thing, this actuator, has noise. After all, this coil is a wire, and it's coming through a resistor, and there's Johnson noise through the resistor, and it's actually coming through worse things than that. And the noise is producing current going through the coil, and that current going through the coil is noisy, it's random jitter, and that random jitter is pushing and pulling on the magnet. That's bad, because we only want to push and pull on the magnet when we want to, and not with noisy actuators. How much is this noise? Well, if you want to get quantitative here, what we're going to do is we're going to set things up such that at low frequencies, below the LIGO band, or maybe at the LIGO, up to about 100 hertz, we're going to push and pull and control the mirror. But at higher frequencies, we really don't want to. So we put a filter, which is a low-pass filter, and which eliminates the noise, effectively eliminates it above about 100 hertz.
The rule of thumb on those things is about 1 nanometer of noise at 1 hertz with forward f to minus 5. F to minus 5 roll off.
There you go. Well, we'll get more quantitative maybe later in the course. Yeah.
Why do you have to touch the mirror again?
Why do we have to touch the mirror?
It looked like you just made a nice arrangement that doesn't.
Oh, no. You see, here's the mirror, and here we're touching it.
Right, but the magnet's not actually connected to anything external.
True. So the magnet is not being touched. But this mirror has a normal mode.
You can't build that in.
And if you touch it with this, you're messing up its normal mode. It's just like putting a little knob on a bell that doesn't belong. Messes it up.
So we want to get rid of the magnets in
advanced LIGO. That's right.
They're a real nasty thing to have there.
That's right. But for initial LIGO, we live with them. In advanced LIGO, we'll have quadruple pendulums. The mirrors are very, very quiet now. We need to push them only a tiny amount. You could actually use a laser to push the mirrors. That's called photon drive. Okay. Next generation will be graviton drive. I don't know, or a tractor beam or something. I don't know. But no, we're exploring actually two techniques: photon drive and capacitive drive. So you put a little plate, fraction of a millimeter away from the mirror, and then put charge on it to push and pull on the mirror, because the mirror is a dielectric. So you can do that, but you're talking pico-Newton or femto-Newton forces. Okay, so here is your test mass. Here's that standoff, looking on the side.
Question.
Yeah.
If you were to use a laser now instead of the hand, how powerful should the laser be?
If you want to use a laser to do what?
To push the mirror now.
To push the mirror now. So we're talking about needing to push the mirror by as much as, many, many nanometers. So we need like nanonewton or better, micronewton type forces. This, let's see, it's a CO2 laser, a standard thing that you can buy, can do piconewton forces. So we need something 1,000,000 times stronger. Yeah. Yes, it would heat the mirror. Oh, yeah. Want to avoid that if we can, except in advanced LIGO where we try to build it such that we really don't need that much force at the bottom, at that mirror at the bottom.
Yeah, I was hoping this laser would be the same as the laser inside LIGO.
No, it would have to. The laser inside a LIGO is producing radiation pressure, which is moving the mirror, but you need something much more powerful. Sorry?
That's smaller. Why don't we move on? It'll be smaller.
Yeah, that's right. Okay, let me just talk about a control system here. Here's our coil, here's our magnet, here's the sensor over here. The sensor, which is this LED pair, is sensing the motion of the mass. That can go into some electronics and then go back and feed on the coil, not to position the mass in exactly the right place, but just to stop the mass from swinging back and forth so much like it likes to do on a pendulum. We can dampen swinging. What you do, you take this position sensor and you differentiate it electronically. And you get a signal proportional to velocity. And you feed back on the coil to reduce its velocity. This is velocity damping. And the effect it has is beautiful. It kills that resonant peak without putting much excess noise in the wings. Okay? And so that's just local velocity damping. It's not putting the mirror where you want it to be. To do that, you need an outside signal, a length sensing and control signal, which comes from the potentiometer. You combine that with the global, that is the position of this mirror relative to that mirror 4 kilometers away, combine the two and push and pull on the test mass through the coil. That's the simplest control system that we have. It gets complicated though, because each mirror has 5 of these magnets and LED photodiode pairs. They all go into, they all get digitized. It all goes into a digital feedback system, which can put in differentiators and band pass filters and low pass filters before it ever goes to the coil drivers to control the mirrors. And it goes through a matrix which converts 5 LED signals from 5 different places around the mirror to position, pitch, and yaw, and then converts it back to 5 coils. Then we have screens that control these things all over the place. I just was going to flash that. Okay. Now, in LIGO, we have, as I pointed out, a lot of degrees of freedom to control. And considering only the length and not angular degrees of freedom, we have the arm lengths, we have the Michelson, and we have the power recycling cavity. And we can combine them. We usually combine them. L1 plus L2 is the common mode, and L1 minus L2 is the differential mode. That's the gravitational wave. And then here's the average of these two lengths is the power recycling, and the difference between these two lengths is the Michelson. And all of these are controlled. 4 interferometer lengths controlled with 4 sets of sensors and actuators. And there's also 10 mirror angles, and pitch and yaw for 5 different mirrors. There's actually 6 mirrors there, but one of them is sort of a reference, and all the others are moving with respect to it. So it's a large control problem, and if I had time, I would talk about control systems, but I don't have time to talk about control systems. They're fascinating things, and in particular, the key about them is that you understand a control system by its frequency response, because you're controlling noise, and noise is random, and the only thing that's not random about the noise is its frequency spectrum, and therefore, to control it, you have to study its frequency response. And I don't have time to go over this, unfortunately. So I better stop.
We can do that at some other point. I might, in fact, ask you to come back and do it. Thank you very much.
I obviously couldn't cover as much as I would like to.